Hey guys, hope you're all doing well. Today we're going to talk about section 5.2, all about angles in trigonometry. So we'll be talking about radians, degrees, the unit circle, what we can do with these types of problems, and all of that good stuff. So hopefully you've read through some of the chapter. I will only be covering a few parts of it and a few examples in this video. So the first thing I just wanted to talk about was radians. I know it was kind of a tricky subject to look at, and we really need to understand what radian or radian measure is. So the radian measure of an angle is the ratio of the length of the circular arc subtended by the angle to the radius of the circle. That is a lot of big words. So let's kind of break that down. So if we have a circle, let me draw one right here. So if we have a circle, it's talking about the angle of the ratio of the length of the circular arc subtended by the angle. So let's go ahead, we'll find the middle of our circle here. We'll draw our initial side of our angle and our terminal side, and this is what creates the angle. So the radian is this ratio of the arc length, so the length of the circle between those 2 points, compared to the side length, otherwise the radius of our circle. So we'll call this arc length S, as it is denoted in your book. So it's just the ratio of this arc length compared to your radius. So that is written right here as your equation. All right, so if the circle has a radius of 1, then your arc length divided by 1 is just the same thing as your arc length. So on the right side, we have your unit circle, and this is how we were able to find the radian measures of all of those different angles. And we'll walk through that in just 1 second. So the radian measure, because it's the ratio of 2 separate lengths, we call it a unitless measure. So we don't necessarily need to write the word radians or rad for short after the measure. However, it can help sometimes. So if you ever see a unit of measurement that doesn't actually have a unit behind it, then we're going to assume that it's radians. Whereas with degrees, we'll always see the degree symbol, or it'll say the word degree afterwards. So just to know, in a circle consists of 2 pi radians. Let me write that. So just like a circle consists of 360 degrees, it is consistent of 2 pi radians. And this is because if we find the circumference of the circumference is 2 times pi times your radius. And on a unit circle, our radius is equal to 1. So on a unit circle, our unit circle is consistent of 2 pi radians. If we look at, let's look at an eighth of our circle. So if we're trying to figure out the radian measure for this guy, we know we have 45 degrees. 45 degrees is 1/8 of 360 degrees. So if I take 1/8 times my full radians times 2 pi, I get 1/4 pi, otherwise pi over 4. So this is how we get the radians around the unit circle. All right, let's move on to talk about the arc length on a circle. So the arc length is the length of the arc along the circle. So it's that short part of the circumference around the circle along the radius subtended by the angle theta. So subtended, this is the second time we're hearing this word. It just means drawn out. So if we once again have a circle, and we'll have our initial side here. So subtended just means I draw the terminal side of our angle. And the arc length is what is drawn here in yellow. It is just the length of that section of the circumference. We can find this by using the equation. So our arc length is our radius times theta. And theta, it's really important, has to be in radians for this to work. So, for example, Mercury orbits the Sun at a distance of approximately 36 million miles. In one Earth day, it completes 0.0114 rotations around the Sun. If the orbit was perfectly circular, what distance through space would Mercury travel in one Earth day? So, think about this. We have the Sun right here in the center, and we have our planet Mercury. Oh, that was a dark purple. We have our planet Mercury orbiting the Sun. We want to figure out in one Earth day, how far did Mercury orbit around the Sun? So to begin this, we see that we have rotations, but our equation, we need radians versus just one rotation. So we know that in a full rotation, there are 2 pi radians. So one rotation equals 2 pi radians. So I know in my problem that I had 0.0114 rotations. So I'm going to go ahead and multiply that by 2 pi to convert it into radians. And this is where I get 0.0716 radians. So now I know my radians, which is my theta value. My radius, I was given 36 million miles from the Sun. So now all I have to do is use my equation, arc length equals radius times theta, to figure out my arc length is 36 times my theta value of 0.0716, which will give me an arc length of 2.578 million miles. So I'm just going to go million miles. It is really important, especially for these problems that we're talking about distance, to include that unit of measurement if there is one. So remember, with radians, we don't necessarily have to include it, but when we're talking about distance, I need to know what we're talking about. Are we talking about 2.57 inches, or in this case, 2.57 million miles? So just make sure with these problems, you are always talking about the unit of measurement. Another thing to note, once again, theta has to be in radians. So if we're given rotations, like we were in this example, we have to multiply by 2 pi to convert it to radians. If we're given degrees, we're going to have to convert the degrees to radians first in order to solve this problem. All right, so go ahead and do the try it now problem after example 9. Once you are done with the try it now, problem number 5, go ahead and read through the area of the sector and complete the try it now problem number 6. So, now I want to talk about angular and linear velocity. So this is something that might be brand new for some of you guys. If you've ever taken a physics class, you'll probably know a little bit about this and maybe recognize some of the equations. So as a point moves along a circle of radius, its angular velocity can be found as the angular rotation theta per unit of time, t. This w in the equation is read as omega in the Greek world. So this guy is omega. All right. So the linear velocity of the point can be found as the distance traveled, so the arc length per the unit time. So it's important here to just kind of remember that the angular velocity will always be something per unit of time. So for example, it completes something radians per minute. So it'll always be something based off of that angle. Whereas linear velocity is distance. So if I say I travel 50 miles per hour. That is a linear velocity. So, leading into example 11, we have a water wheel completes one rotation every 5 seconds. We need to find the angular velocity in radians per second. So, we're given how many rotations it completes and in the time it completes. So we know that t equals 5 seconds. All right, we also know that one rotation is the same thing as 2 pi radians. So, if we want to calculate the angular velocity, our angular velocity, omega, is going to equal our radians. So since it completes one rotation, we know that's 2 pi radians. So 2 pi over 5. Once again, we want our unit of measurement, so we have 5 seconds here. If you would like to write radians with the 2 pi, you're more than welcome to. So our linear velocity is 2 pi radians over 5 seconds. Or, if we actually divide this out, that is going to equal 1.257 radians per second. All right. Below it starts walking through how the arc length equation, this S equals, so our arc length equals the radius times theta, which is our radians, can be used to figure out and solve for a different way to figure out linear velocity. So this is giving us, you can kind of read through this, that our linear velocity also can equal our radius multiplied by our angular velocity. So we have here our linear velocity can also equal our radius times our angular velocity. This gives us just two ways that we can solve for linear velocity dependent on what we're given. So if we're given the arc length, we'll want to use this equation up here. If we're given angular velocity, we'll want to use this equation down here. So with linear velocity, it just depends on what we know. So let's go ahead and look at example 12. So we have a bicycle has wheels 28 inches in diameter, and a tachometer determines the wheels are rotating at 180 revolutions per minute. We can think of that as rotations per minute. So we need to find the speed the bicycle is traveling down the road. Because we know what the revolutions per minute are, think about that as going around in a circle, which is relating to the angle. So we have an angular velocity, and so we need to figure out what the linear velocity is, or the speed of the bike is. So we need to figure out if it's going 10 miles an hour or however long we need. So the first thing we need to do is convert these rotations into radians. So a couple of the equations that we need to remember is that our angular velocity is equal to our radians over our unit of measurement. We also have that the linear velocity is equal to our radius times our angular velocity. So because we have revolutions per minute, we need to figure out what the radians are. We know that there are 2 pi radians in one rotation. So if we have 180 rotations, we have to figure out what 180 times 2 pi is. And this is going to give us 360 pi radians per minute. All right. So this is what our angular velocity is going to equal now that we have a radians per minute. So our angular velocity is 360 pi radians per minute. All right, now we can use our equation for linear velocity to plug into. So our linear velocity is going to be our radius which if our diameter is 28 inches, that means our radius is going to be 14 inches. And we're going to multiply this by our angular velocity, which was 360 pi radians per minute. So this is going to give us 5,040 pi inches per minute. Once again, it is super important to make sure you are including all of your units of measurement in here. Okay, so the book brings up, you may be wondering where the radians went. Remember, radians are a unitless measure, so if we don't want to include them, we don't have to include them, but we do have to include all of the other measurements. So, we may wish to convert the linear velocity into a more familiar measurement. So this technically is the final answer. We just typically don't look at things as inches per minute. So down here we kind of walk through how to convert inches per minute into miles per hour, which we're pretty comfortable with. So this walks us through 5,040 pi inches per minute. We can multiply this by 1 feet is the same as 12 inches. So we're just multiplying it by, think of it as a giant 1. We're just using different units of measurement. There is 5,280 feet in 1 mile, and then there are 60 minutes to 1 hour. So how this works, if we are trying to convert inches, since we have an inches in the numerator, we'll want our inches term in the denominator, so our inches unit measurement cancels out. If we have feet in the numerator, we want feet in the denominator, so those cancel out, which leaves us with miles in the numerator, and that's exactly what we are looking for the units of measurement. And to convert the minutes to hours, we know that there are 60 minutes in 1 hour. Since our minute was in the denominator originally, we want our minutes in the numerator to be able to cancel out. And this is what leaves us with miles per hour for converting our units of measure.